Hello, everyone. My name is Ira Kemelmacher. I'm going to talk about the work we've been doing in my group at the University of Washington in the last year or so related to human modeling and synthesis. Thanks for listening to this talk. So the first topic that I'm going to cover is a paper that actually appeared on the CVPR that we call Background Matting, The World is Your Green Screen. This is led by a postdoc in my group, Shubdeep Singh Gupta, and Vivek Jairam, a PhD student in my group, in collaboration with Brian Curley, Steve Seitz, and myself. So some of you may have seen this video about half a year ago, maybe a year ago by now. This is a professor talking on BBC about serious situation in North Korea and commenting on that. And then this fun scenario becomes visible in the background behind him while he's on BBC. So let's watch it together in case you haven't seen it.
Scandals happen all the time. The question is, how do democracies respond to those scandals?
And what will it mean for the wider region? I think one of your children's just walked in. I mean, shifting sands in the region. Do you think relations with the North may change?
I would be surprised if they do.
The region.
North Korea, South Korea policy.
So that was a pretty unique situation back then, and really funny. People were actually kind of excited to see it. It's a great family scenario if somebody's doing video call from home. But these days, since we're doing most of our meetings in video calls, sometimes our backgrounds are not as funny, or something we don't want to reveal, or want to have in all our meetings at least. So we've been trying to work on this problem. And so, for example, these days our background may look like this, where maybe we want to remove it. So is there a way to take this background and basically create a green screen out of it? So that's the question that we've been solving in this project and presented in the paper. You'll say, so like one way to do it, right, is just to put a green screen behind us, but that's very expensive, hard and so on. Nobody's actually doing that. But you'll say, hey, but I'm using Zoom, right, all day long, or similar video call software, and I already have this capability. And this is true, but when we do this green screen scenario over Zoom, results may look like this. So for example, you'll notice all the artifacts due to motion, due to hair, due to other effects. And so really we would want to fix all those problems to make a perfect foreground background separation and the background replacement. So this is what this project is about. And this is a comparison on the same video to our results. So you'll notice that there is way less, there's a really nice separation of the hair strands in the neck area. You see, if you compare the two, you will see the nice artifact, like there's no artifacts, motion blurred, doesn't affect the result and so on. And here's a video example of the same with our algorithm applied. Again, check out the hair, check out the neck, check out the what happens during motion. Cool. Another result on the video in the wild in a way. She's standing outside in front of a very different type of background at the University of Washington, actually. And now our algorithm can estimate the alpha and the foreground very nicely, especially check out the hair area. Once we estimate the alpha and the foreground, we can actually put any background. And so here's another background from the UW. And notice that the fountain is actually moving, and she's moving, but it doesn't change the quality of the algorithm. Okay, so how are we gonna approach this problem, right? So there are three types of approaches to to try to solve it. So one that you see on the left here is background subtraction. So background subtraction means that we will try to separate the foreground from the background based on colors or something fancier, but we'll try to subtract the background from the foreground. That can create artifacts due to similarity in colors of the background and the foreground, or similarity in features and so on. The middle one is segmentation, which is similar to what Zoom and similar techniques are doing. And this is where we would try to segment the person out of the background, but the silhouette, as you can see here in this illustration, that the silhouette around the nose and the face and so on is not going to be very accurate. So we're going to segment, but it's not, a visually pleasant segmentation. Lots of artifacts. And finally, the problem that we're going to solve is something called matting, where we would like to estimate the green parameter alpha per pixel in a way that will let us separate the background from the foreground, and alpha goes between 0 and 1. So it's not a binary number. So let's do quick video comparisons of what background subtraction and segmentation means. So ours is at the top, and at the bottom you see a comparison to background subtraction. As a video, you can see how the artifacts really make it not pleasant experience. Similarly, comparison with general purpose segmentation, state of the art for humans, but still you can see the silhouette issues, especially in the hair area. That is not great compared to ours, which is pretty accurate. Of course, we didn't invent the matting problem. Usually what people are doing to solve, to estimate this alpha is they take the input image on the left here, and then they come up with a way to estimate the trim up. Trim up means that every pixel in the image needs to be labeled by, this is for sure background, this is for sure foreground, and then there are all these green areas that nobody knows what they are, and this is where we need to estimate the alpha for. So going from trim up to alpha estimate, this is something that many techniques has been worked on, and we compare to those we compare our results to those techniques as well. Estimating this trim up is actually really hard, and if you do it manually, it means that somebody needs to label per pixel for each input image. And think about a video sequence, for example, where it's impossible to estimate the trim up for every video frame out there in potentially real time in the future and so on. So it's really hard to scale this type of approaches, trim up based. Okay, so the key idea in our algorithm is the following. We've noticed that we were wondering, like, what is the minimal constraint that we can apply without doing trim ups, or so that we'll be able to create a completely automatic algorithm that works on video sequences. What is the minimal constraint that we can require? So here's what we came up with. We said, so let's say that you take a photo of the person that you want to separate from the background, and then you ask the person to leave the frame, and you take another photo. So you have a photo of the background and you have a photo of the person in front of that background. And you don't have to calibrate anything for our algorithm. Basically, we just require an image of a background. For example, Vivek here, who is one of the authors of this paper, is taking the photo just with his mobile phone. So you don't have to be stable or so on. And then our algorithm works in 2 steps. So step number 1 is a supervised learning approach, where what we say is that there is not a lot of data out there for that has ground truth alpha mats, but there is some. And so there is the Adobe data set. It's called the Adobe Composition 1K data set, and it has 450 ground truth alpha mats that we use, and we compose them onto 100 random backgrounds. Now, this is real ground truth data that somebody created manually. It's not a lot, as we know, to train neural nets, but it's something. And so this is our first step, where we say that the input to the network is the frame, a video frame that we want to estimate alpha for. We have the background, and then we have the we also estimate automatic segmentation, which we dilate and like do some morphological operations to make it more ambiguous on the boundary. So given those three, each of those three components is encoded, and then going into a selector, which is later, and then everything is combined together. We call it the context switching block that effectively chooses the input cues. Then all of these go from the combinator, they go to res blocks, and then decoded to a foreground and an alpha map that that we can use as our initial approximation of the desired alpha map. So this doesn't produce exact results, as we will see in the experiments later on, but it's actually pretty good. That's at least something that we can build on top. And so the second step of our algorithm then is again refinement, which we found to work really well. And the idea is the following. So same input as before goes into this step, but now the green box is we call generator Adobe is the one that is coming from step number 1, where we trained it in a supervised manner. And the yellow block is our generated that we want to train. And what we're doing for each input, we're trying to generate our Adobe result, alpha and foreground, Adobe-based, that is the base result. And we also have the generator that we're training, and we're comparing the laws between the two in a way that the discriminator decides if it's a real or a fake photograph. And we can put as many backgrounds as we want into this process to make it as diverse as possible. So that's exactly what we do. That turns out to work really well. For example, here, each column is a different input photo. There's 6 of them here. And the middle row shows the result of step number 1, and the bottom row shows the result after step number 2 of our algorithm. So you can see that the artifacts like these disappear, artifacts that came from the background, artifacts in the hair area disappear, and so on. Some comparison with state of the art, we compared with many algorithms, state of the art from the recent year and before. Of course, it's a widely researched area, and we created a little video that compares all the methods. At the top, you will see, top left, you will see our results after the 2 steps. On the top right is the input, and the bottom shows the different algorithms. And in this case, at the top right, we show result after step 1 of our algorithm. And the top left is after step 2. Note that our algorithm is not a video matching algorithm. It's done frame by frame, which makes it even more robust in our opinion. All right, feel free to check more comparisons on our web pages. Here's the same, like similar types of result, but now we replace the background. So on the right here, you see our grad students being completely natural, and we replace backgrounds behind them. All right, some more results. You can see also the failure cases, for example, on the right here. There are artifacts near the arm. This is when the motion of the background coincides with the motion of the foreground, then there are still artifacts, so there is work to do, and some other comparisons. So in the future, we would love to remove the need for background capture at all. Wondering how to do that. Of course, given the accuracy that it produces, would be great to make it real time. It's not close to being real time at this point. We would like to handle shadows and reflections in a better way, to handle big camera movement. Currently, it allows uncalibrated conditions, but small camera movement. There is code online, and many people have tried it already. So go ahead and try it out if you're interested. Even we even had a collaboration with Microsoft that when they took our code and combined it to create a virtual stage for their Build conference, which was pretty exciting. And in the keynote yesterday by Satya Nadella, he even mentioned that. That was great to hear. And people use it for all sorts of creative ideas. For example, this class at CMU used the code to create to put the person while they're sitting at home in different poses in a 360 panorama, which I thought was pretty cool. So yeah, feel free to try the code and let us know what you come up with or build upon it. We'd love to hear from you. Great. So in the remaining time, I want to just show a few results that from other related works from my group on image synthesis. One is called Lifespan Age Transformation Synthesis. It is led by Roy Orel, a student in my team, Shumdeep Singh Gupta, Ohad Fried from Stanford, and Ali Shahmar from Adobe, with myself. This is a new work that didn't appear anywhere yet. So the idea comes from our long goal in my group to try to solve the problem of how do you predict how a child looks like in an older or younger age. So this is what we want to achieve automatically with image synthesis. So here's an example rendering, and in particular, why we're interested in that so much is because of the Missing Children organization that came to us and said that this is actually an amazing, could be an amazing resource to help find those kids. So we've been working on that for a while now. Of course, it's also used, such synthesis also used in movies and ads and other ideas. This is a sample from The Irishman, a recent movie where they made De Niro look younger with the computer-based methods. The key challenges in such a work, how would you synthesize, is first of all, there is lack of data, in particular when we focus on children, there is lack of data for the full range of 0 to 100 ages. And so, and there's really limited ways of how we can achieve collecting such data because of the, the full span of the ages. It takes years to collect such data. Additionally, when we talk about children, image synthesis is there is a dramatic head shape changes as opposed to just texture. And so this is why state of the art typically focus on taking an adult, adding wrinkles, doing some texture changes to be able to create more an elderly person, while the other part of the head shape is actually a really hard problem, and this is what we focus on. And it's particularly needed when we're trying to create aging of child to adult. And of course, ideally, we want to make it as efficient as possible and create a single network for any age to age, as opposed to pairwise connections. That it means many permutations of those and many networks. So I'm not going to talk a lot about the algorithm. Feel free to check out the papers on the web pages. But one big contribution that we invested in and we made available on GitHub is we took FFHQ, which is a great data set for face modeling that StyleGAN is using and other state-of-the-art image synthesis algorithms for faces. And we labeled the data set and we provided gender information for every photo. Every one of the 70,000 photos, we provided age group that was labeled manually by people working with a labeling company. we provided head pose, glasses type, eye occlusion skull, and full semantics map, which is 19 classes for the different face components. So feel free to use it not only for aging, but for other ideas that you may have. The cool part after we did the manual age labeling is that you still see a bias in this data set in the 20 to 29 age, but what we do notice, even the little blocks, there is around 1,000 photos per gender per age group, which is pretty good, and this means that we can train good GANs on that data now that we have it. And indeed, we came up with a multi-domain GAN that allows us to separate between identity and age, have separate latent spaces for those, and use the most recent ideas from StyleGAN2 and others to be able to design a network to synthesize age. I'm not going to go into the details, but I'll show you some results. So each of those photos here is a little movie where you can see a person synthesized for ages from baby to elderly, completely synthetically using our algorithm. Some interesting things to notice, for example, the bottom left here, you can see how the teeth appear and become from child's teeth to adult's teeth. You can see how the eye shape changes. You can see how hair grows and other effects that appear with age. And we have many more results on the webpage, so feel free to check it out for many different people. And the last paper that I want to show the results for is our focus on, we've been working quite a while on sports reconstruction and excited about this area. And so the recent work that we have in the works now is reconstructing NBA players. This is led by Lu-Yang Zhu, a grad student in my lab, and Konstantinos Rimatas with Brian Curl, Steve Seitz, and myself. This is a very new work. So the idea is that can we take a single photo and be able to reconstruct the person so that we can later render them from different viewpoints, different camera position, or in 360 view of full, being able to capture the shape, the texture, the minor differences when, you know, in basketball, what happens is that the poses are very extreme. It's very non-generic human type of poses and shapes. So we would really want to focus on that domain and see how we can get with the best results we can. And I'm not going to talk about the algorithm, I'll just show the results. For example, from this single photo of taken online, this is the result that we are able to achieve. Again, a different input photograph and the results. Notice the similarity in pose, in body shape, in and in the realism quality. We have compared, again, not getting into the details here, but we have compared with state-of-the-art in human reconstruction from single photos or from videos, including PIFO and PIFO HD and all the state-of-the-art methods out there, and provide that in the paper and on the webpage. Check it out. For the basketball domain, even if we trained on our data and we use video game data, our algorithm outperforms state-of-the-art. All right. I will finish here. I would like to thank you for listening. I talked about 3 methods, recent work from my lab in the last year or so. Please feel free. I talked about matting. Please feel free to talk with Shumdeep if you have questions. Try out the code. Tell us what kind of cool things you came up with based on the code. I mentioned the aging algorithm and the new data set that we provided. Feel free to contact Roy for more information there, and all the other authors, of course. And I also showed our new results in basketball domain and reconstruction, 3D reconstruction of humans. Lu Yangzhu is the lead author on all those results, and we should have the data and the methods out there soon on our web pages. So check it out from time to time. It's not there yet, but it will be available soon. Thank you so much. Check out also realitylab.uw.edu. This is our lab, and there is a lot of excitement, advancement there in computer vision graphics, VR, and AR. All right. Bye.